Okay, let me get the computer set up. So I'm very pleased to be here and I appreciate it. It's a little bit funny from the GPU side for me to be the speaker from Maryland because I've not been the leader of our effort. So part of the reason I'm the one here is because I actually got a degree in astrophysics. Okay, my screen is blank, so I have to look over there. Half second. Doesn't happen with Macs very often. And I was a graduate student here at Princeton from '88 to '93. And if you think about it, that was a very critical time because that was the time that there was this flourishing of parallel computers which were going to change the world. And so many of my colleagues, many of my graduate student colleagues, worked on machines like the connection machine, various Intel products, and there was a great deal of excitement, and these computers could outperform the sort of standard issue Cray supercomputer of the day. But then midway through the time that I was working, I saw all of this technology collapse and only a couple of winners emerge. And not only was it a hardware collapse, but it was also various ways of programming, different extensions of Fortran or C came and went. And so my view of this was very skeptical when I first heard about GPUs because the last thing I wanted to do was invest in a technology that was going to disappear rapidly. So I got to be excited about this. I'm in the Department of Physics at the University of Maryland. I'm running a center called Multiscale Plasma Dynamics, and our focus is on doing large-scale astrophysical and laboratory plasma physics simulations to understand primarily turbulent phenomena. And so turbulence is a wonderful problem that is very computationally intensive. I looked around and found out that we had a lot of experts on campus at the University of Maryland. Ramani Duraswamy, Neil Gumarov, Amitabh Varshni are all professors. George Sanchez is a postdoc. And I'm working with Elliot Quatert and Greg Howe, Steve Cowley on the astrophysics side. Ramani, Neil, and George are all here, and Neil's going to give the second part of this talk later this afternoon. So what I'm going to give you is an overview as an application person who's looking at a new technology which can potentially accelerate my workflow. Does it actually work? What kind of experiences do we have? And what would I recommend? And where are we going at Maryland? Some of the experts in the actual computer science issues are these people, and I encourage you to talk to them as well. And Neil's going to give a lot more of the computational details in his talk shortly. This is very disconcerting that I can't see my screen. Okay, so the overview is I want to tell you a little bit about the effort at Maryland because I think some people come to a meeting like this to find out, should we get in the pool? Is the water comfortable? And really what I want to talk about in my talk is how we're answering that question at the University of Maryland. Then I'm going to give you some idea of the working physics algorithms that we have. They are the fast multipole method for in-body calculations. You can use it for other uses. The technical details of this are the most interesting part of what we're doing at Maryland today because this is a custom algorithm that you can't use a lot of the built-ins that come with CUDA. But these guys have got it working extremely well. So I think the experiences we have here will be very interesting, and that will be the second talk this afternoon. We also have pseudospectral code for turbulence, and this is what I work on. I've ported code successfully to CUDA using this technology, and that's what I'm going to talk about in my talk. We also have some particle and cell methods, which are very common in plasma turbulence, particularly in laboratory applications. And the results there I'm going to tell you about that. We also have experience at Maryland because people weren't interested in astrophysics first, they were interested in graphics. We have experience in audio and visual computing on GPUs. There's a group in computer science doing optimization. We have large-scale visualization algorithms and so forth. So we have a sort of broad experience base. And the results, then I'm going to tell you a little bit about the results of integrating these different groups together to try to use this technology. And the fundamental thing is that we found we needed a middleware library somewhere in between the existing high-level codes and the CUDA interface that's provided to really make it possible to rapidly develop physics applications in particular And so we wrote one, and it works quite well, and we're happy to work with you if you want to use it too. And then tell you a little bit about where we're going. Okay, so I think in the great scheme of things, Illinois has probably the largest GPU effort among universities, and I think Maryland is somewhere next. We have an NSF-funded CPU-GPU cluster with 30 nodes, something like that. Each node currently has a couple of CPUs with a GPU, a couple with Ethernet and InfiniBand MirrorNet, 10 terabytes of storage, 3 gigahertz Xeon processors, and then for the GPUs, they were purchased at different times, so we have various models of the GeForce, GTX, that kind of level of GPUs. And then we also on our campus several standalone computers, all using whatever these guys are willing to sell us at the latest possible time. So we have several on order, which tells you we're happy with the technology. We're still buying it. And we're upgrading this cluster this winter to a 2.0 with all new GPUs and also upgrading other aspects of the machine. So this is a several-year project funded by NSF that got a lot of people on campus excited. Who's currently involved? Well, the effort began in UMIAX, which is the University of Maryland Institute for Advanced Computer Studies. Had to say that since we're at the Institute for Advanced Studies here. There's been a recent broadening of that focus to include people from physics, astrophysics, and what we're doing is we have weekly meetings, 5 to 20 people, depending on what's up that week, where we sit down for 2 hours and talk about this technology, and we have informal talks. There are undergrads, grad students, postdocs, all getting more involved. And the important thing here is these are not computer scientists by and by. There are some. But I think what's different about what we're doing at Maryland is if I'm working if I work on an astrophysics application, I'm happy to go down the hall and learn something from my computer science friends. But I want to keep my code accessible to me as a physicist. I don't want there to be large sections of the code that I can't understand, read, and so forth. So my goal here is that my graduate students and postdocs can actually use CUDA without employing too many computer scientists to do any hand coding. And I'm happy to say we're able to do that because this interface looks good. We have funding from several agencies, and the current astrophysics projects we have going are turbulent heating, which I'll show you a result or two from, and also Manuel Tiglio has just joined the faculty at the University of Maryland doing numerical relativity calculations, and we have a code of his which we're porting to the GPU just to see a different kind of code in action. And we have one novel component at Maryland. The HPC Software Engineering Group is funded by DARPA to measure for other computer systems development time, categorizing common program errors, comparing with and they're doing this now with our GPU efforts. So we have everybody that's programming in GPU, at least in the physics and astrophysics, is working on instrumented computers. So their development time is being measured, their bugs are being counted, and we're trying to get an idea of whether this is actually, because look, it's important. You give me a 2 teraflop machine for 10K, but if I can't write code in it, or if my students can't write code for it, I don't want the computer. That's what I learned back in the 80s. And so we're trying to measure that and come to a sort of decision about that. So the key questions that we're addressing: how stable is the hardware-software platform? And in a short talk, I'm really trying to give you an introduction to these ideas from our point of view, and I encourage us to have discussions. 5 left? Okay. So I have to go faster now. So how stable is the platform? The answer is very stable. I think we started at version 0.5, 0.6, something like that. I've been going through, and forward compatibility has been good, or backward compatibility. Which major algorithms can successfully exploit? These are the things we're asking. What is the development? This is the most important question for me. What is the development and maintenance path for porting large-scale applications to this platform? Can we do it with a finite amount of resources without wasting too much time? And at the end of the day, do we get physics results, astrophysics results, faster than waiting on a slower computer but with existing code? And our roadmap is we're aiming for a $1 to $5 million purchase next year, and we're trying to figure out, should it be CPUs, GPUs, which vendor, that kind of thing. So I mentioned to you, and given the time, I'm just going to briefly point at this slide. Ramani is here. Ramani Duraswamy is actually doing this audio-visual GPU computing. So it's not just physics and astrophysics, and we have the same people in the room sitting down and talking about programming the thing. So I think we have a good perspective on what's possible. The turbulence problem is what I do. This is a picture of a simulation of fusion turbulence. These are isocontours of density fluctuations. And we've been doing these simulations for a long time. Recently, we've started to use the same kinds of calculations that we developed for fusion turbulence calculations to look at astrophysical plasmas. This is work with Elliott Quateric and the Berkeley group. And this is a measurement of solar wind turbulence by Stuart Bale et al. These are two different ways of analyzing the same data. The upshift, don't worry about the fact that one's higher than the other. It's arbitrary units. The key thing is that the green curve, which represents the electric field fluctuations, pulls away from the black curve, which is the power spectrum of the magnetic field perturbations measured in the solar wind. And there's some scale at which this happens. And there's all sorts of interesting physics going on about that, which has implications for accretion flows, interstellar fluctuations, scintillations, all sorts of interesting phenomena. And we'd like to understand this transition. So the business that I'm in is doing large-scale simulations. These are first principles calculations, roughly 1 billion mesh points, thousands of processors for 100 hours, and we're getting, green curves that do the right thing, magnetic field fluctuations that do the right thing. So this is the kind of work that we're trying to do, first principles or ab initio, depending on your community, direct calculations. These are too big for a GPU right now. Okay? What we want to calculate from those fluctuations is a sort of typical heating function. Which one's getting heated by this turbulence? Ions, electrons, minority component of some kind. And then we want to put it into a calculation such as done here by Goldson and Quateric to look at the luminosity function coming out of an accretion flow. This is our target. The kinds of calculations we're doing require, these are processor numbers up to 1,000 for this figure. They require thousands of processors. This is the time for a calculation for a single time step on several different computers. So we're using IBM SPs, Blue Gene, Dawson is an Apple cluster, Bossi is an SP, and Franklin is a new Cray XT4. All of these runs are exactly the same input file. So these are strong scaling results. We have a problem that can run on one processor up to 1,000 processors and get roughly 1,000 times speed up. So we know how to write parallel code that takes advantage of 20 and 50,000 processor machines. We can easily go to much larger problems if we don't insist that if we did a weak scaling plot, we can go to tens of thousands of processors. This is a strong scaling plot. So our goal is to find out the overriding question that I'm trying to answer is, can we get to the GPU goal of doing this same problem significantly faster? And here I would be counting GPU nodes, not GPU processors. And given the short time, the interesting question is we can do this point right here on a somewhat smaller problem, but it scales appropriately. We're prototyping code right now. We get this speed up. So if we can use multiple GPUs together, we'll be able to outperform thousands of processors on a Cray with hundreds of GPU nodes. And this will be very happy because they're much cheaper. We can put it in our own building. So let me tell you a little bit about how that worked. Here's the calculation behind that calculation. What we have is a plasma turbulence calculation that's a prototype of the larger one. Instead of the full dimensionality, we did a 2D calculation. And the curves here are time to do the calculation versus the size of the problem. And this is on a log plot. And so the expected scalings of the lines here. And the CPU curve is here. The GPU curve at small problem size has enough overhead and latencies and so forth that it doesn't perform as well. But at large problem size, the GPU gets to the expected scaling, and the ratios of the high performance parts of the curve is a factor of 25. So we're getting a full factor of 25 speed up on an existing plasma turbulence code that does a problem that people know about. The great thing about this is I was able to write this code. I am not a GPU expert. I was able to write this code in one day and get the full 25 times speed up using this experience. I know a lot about GPUs, but this was my first time to program. I had no class in GPUs. I just looked at the manual and used this middleware that we've developed at Maryland to make it easier to get all of the performance enhancements you need from the memory latencies and the various kinds of issues that come up directly on the GPU, you can get that, and so we're very happy with this result. So the summary of our performance results, and let me remind you again, so this code is an MHD code. It gives you 25 times speed up. The nonlinear PDE, it's typically getting its bang from Fourier transforms, which are in CUDA. Data parallel structure. It's very easy to exploit that kind of problem and get it onto the GPU and get an impressive performance improvement. There's an in-body force calculation with fast multipole method on a GPU. We can calculate, for 1 million masses, we can get all the forces in 1 second. This is extremely fast. It's the whole talk coming in about an hour from Professor Gumarov. So I'm going to let him tell you about that. There's a lot of lessons learned there that he's going to go through in more detail. But this was a problem that demanded a lot of understanding of the memory hierarchy of the hardware, and it's a custom algorithm. We're not using QFFT, QBLAST, those kinds of things in the same way that you can on a simple, but nevertheless you can successfully exploit and get that kind of performance. We also have a particle and cell code. Currently our best effort is 20 times speed up. We're also getting in the range of 10 to 20 times speed up. The issues here is that you have to really focus on getting coalesced right to get the best performance. If you don't need to sort the particles for some reason, you can get 100 times speed up. But particles are moving around, and the memory accesses get to be very expensive if things get too fragmented in memory. So you actually have to have a way of keeping that together. And so we're still working on trying to get better than a 20 times speed up out of that kind of algorithm. Our key early finding that I said before, that we needed another layer to support easy porting, debugging, and maintenance. These were the things that we found hard on the GPU that we addressed, and we would like to see more from the vendors in this direction. And I'm happy to talk about more of that in the workshop. We have 2 posters. One of the posters will be specifically about this, and it's going on to Supercomputing 07 to be presented there. So the roadmap, I think I'll just leave this up here and leave the rest of the time for questions.
Very good. Thank you. Yep.
I just saw you flash up the support for Fortran 9X.
Yeah.
Exists.
Yes. Yeah. So we're right. So here I am. I'm a physicist, astrophysics, whatever. I don't want to learn CUDA. I mean, it's great stuff. Wonderful. I have been writing code for many years. I'm a computational physicist, so I'm not afraid of the computer, and I've written a lot of large-scale code. I wrote Fortran 95 to get the code ported into CUDA. I had to write 10 lines, literally 10 lines of CUDA, maybe 20, something like that, in order to support the actual. We'll show you in the poster the details of how this works, but at the end of the day, I'm writing Fortran. I have to supply a little bit of CUDA under the hood, but I don't have to learn CUDA. There's a whole bunch of issues which we've hidden with this wrapper. So I was able to write that code without reading the manual. So yes, Fortran 9X support I think is reasonable to expect. That should be easier, but actually some of the issues we used essential features. What we did was we built structures. And so instead of variables, you're dealing with whole structures, and all that information is hidden there. So I wouldn't try to do it in 7X or 6.
Maria? Somewhere down. Oh, and Brian.
Yeah, double precision. You don't need that in your code.
All of our calculations have always been double precision. And so one of the big questions I had when I looked at this was, why in the heck am I going back a step and looking at single precision? And I examined sort of my soul, and I realized that turbulence, if I think I need too many digits for figuring out what's going on in turbulence, I'm fooling myself. I mean, it's true that I use spectral algorithms. I'm pretty uptight about getting all the accuracy I can get. And there will be some applications which that's necessary. But my view is that the hardware will come for that. Actually, we have a grad student who's at NSA, and I can't tell you what that stands for, who's doing an extension of CUDA to high precision as it exists, so that we may use those. But I figure the vendors will beat us to that.
Anyone else? Okay. Well, thank you again.
next speaker is